Hello, everyone. My name is Yuzhe Tang. I'm an assistant professor in the EECS department at Syracuse University. Today is my pleasure to introduce our work on cost-effective data feeds to blockchains. This is joint work with my student Kylie Jiaqi Chen from Syracuse University, Zhehu Yuan from New York University, and our collaborators, Dr. Chen Xu and Jianliang Xu from Hong Kong Baptist University. To start with, our work focuses on a type of a blockchain application that is called DeFi or decentralized finance. This year 2020, we see exponential growth of DeFi application deployed on Ethereum and other blockchain systems. Important primitive used to construct a DeFi application is data feeding. A data feed allows a blockchain application to see external world data. For instance, a stable coin, like make DAI, needs to read, running on Ethereum blockchain, needs to read the exchange rate between Ether and US dollar in order to make liquidation decisions. For another instance, TBDC, which is a Bitcoin packed token, allows a Bitcoin owner to do business or transaction with Ether owner on Ethereum platform. In order to run TBTC, Ethereum needs to read newly mined Bitcoin blocks. So this requires essentially a data feed called a sidechain. Today, data feed is a multi-million business. For instance, Chainlink, as shown on this diagram, Chainlink need to pay about $1 million per month in order to maintain its daily operation of data feeding. So the goal of this work is to optimize the cost of data feeds. In order to understand where the cost is spent, let's take a look at the two baseline designs. In the first baseline design, what we call BL2, it is a push-based data feeding. In this case, the off-chain data producer pushes data to be stored on blockchain. In this case, there is a data replica stored in the smart contract storage. The second baseline, BL1, is based on the pool design. The smart contract, which needs to read the data, will try to send a request to off-chain data producer and try to pull or retrieve the data from the producer. In this case, there is no data replica maintained on the blockchain. In both baseline designs, the decision whether to replicate the data on blockchain is static. In other words, such decision is always the same and does not change with the workload. On the other hand, we observe in real DeFi applications, workload changes dynamically, and particularly the data access pattern varies a lot. For instance, in MakeDAO's price feed, we did a measurement study with the result plotted in this figure. The x-axis looks at the sequence of writes, each triggered by a price tick in the data feed, and the y-axis looks at the number of reads are following a write. You can see most of the time, there are few reads following a write, but occasionally it can be as many as hundreds of reads after the write. So we observe a gap between the dynamically changed workload and the underlying system design that is essentially static. To tackle the problem, the key idea in this work is dynamic data replication scheme built on Ethereum to optimize the data feeding cost. In our vision, the system should intelligently switch to baseline 2 if the workload is read intensive, and the switch to baseline 1 if the workload is write intensive. By doing things this way, it avoids the cost problem incurred by those static designs. With that, we propose GROB system, gas efficient data replication on blockchains. GROB system is a middleware that runs across data producer, service provider, and blockchain nodes. Okay. In our system model, we also additionally consider data consumer smart contracts. The Grub middleware system exposes two essential functions in its API. A GGET call allows a data producer to upload a batch of recently produced data rights. And a GGET call is issued by data consumer smart contract. It may retrieve the data stored from off-chain to the blockchain. Internally, the Grub system consists of 3 planes: data plane, control plane, and security plane. In the data plane, each data record is either replicated or not replicated. When it is in the state R replicated, there are 2 data replicas. The data is by default stored off-chain in the key value store on the service provider. Additionally, data is also replicated to the smart contract storage on the blockchain. Accordingly, there are 2 programs managing the 2 replicas. The control plane makes a decision whether a data record should be replicated on blockchain. And it runs on data producers. So the data producer first monitors the workload, and then based on the workload, it makes such a decision whether the data record should be replicated. In the security plane, the main adversary of Grub is the service provider, which can forge the data records uploaded by the data producer. In order to prevent this attack, we apply ADS protocol, authenticated data structure protocol to Grub. Particularly, we build 2 Merkle trees to authenticate the data records of these 2 states, replicated or not replicated. In the control plane, we propose a series of online algorithms. Each online algorithm, given a read-write history, the algorithm decides if the data record's next write should be replicated to blockchain or not. The intuition we use to design the algorithm is the following. If the record is read heavy, then we try to replicate it. Otherwise, we refrain from replicating such record onto the blockchain. In the paper, we prove the online algorithm achieves 2 competitiveness. That is, the cost of the online algorithm will be bounded twice the cost of the optimal offline algorithm. We build a prototype on Ethereum and we open source our system. Our system passed the middleware 2020 artifact evaluation. We did the evaluation, cost evaluation on the real world trace. So this trace runs 5 days, and it's the data records is collected from the ETH price oracle. So the result shows that Grub achieves 11% of the gas and 64% of the gas compared with baseline 1 and baseline 2. We did extensive cost evaluation on a real trace built from the Bitcoin packed token and mixed YCSB workloads. With that, I would like to thank everyone for your time. If you have a question, please send it to my email at this address. This slide is also shared on my personal webpage. Thank you.